Okay, what I want to do in this screencast is to go over the take-home quiz. Um, just a couple things here. Let's just use red. First of all, this H should be capital, really. CH3. That's a very funky. Should be CH3, CH2OH. That's just ethanol. For some reason, it didn't come out the way I wanted it to. But anyway, you understand that this is ozonolysis that's going on an alkene. And we've talked about that as a method of preparation for the carbonyl compounds. And so recall that the ozone is going to cleave off the double bond. And what you're supposed to do is put a double bond O on each side of that double bond. So you're going to see something like double bond O, and then bond, 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 another double bond O, and 3 carbons for that. If you want, you can always just number this as 1, 2, 3, 4, 5, 6, 7, 8, and 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. I didn't create matter. I've shown the cleavage of the double bond. That's my answer. The next question was that you're given a ketone and you're treating that with hydrazine with KOH. Recall, this is the Wolff-Kishner reaction. Wolff-Kishner reaction. And the product of this reaction is that using the hydrazine, the C double bond O essentially undergoes reduction. So you're going to end up with 1, 2, 3, 4, and 5, an alkane, which will contain 5 carbon atoms. So pentane is your correct answer. The next question is that you are given a diene, and we are subjecting that to KMNO4. Realize KMNO4 is a very strong oxidizing agent. It's like I have said umpteen number of times, it's a punch in the face. It's going to oxidize, and it's going to oxidize both of these double bonds. Anytime it's a terminal alkene, that aldehyde will go all the way to the carboxylic acid. However, if it's a ketone and if we are not heating it, then that will stop as the ketone. So you're going to end up with a double bond O on this side plus another ketone, giving you a carboxylic acid on this side. And the third product will be, and I'm just going to put the numbers so you can follow it. 1, 2, 3. Those are right here. Then we have 4, 5, 6, 7, and 8. This is 4, 5, 6, 7, and 8. And I have 9, 10, 11, and a 12. Let's call that 9, 10, 11, and a 12. If where I have carbon number 10 and where I have carbon number 8, if those happen to be hydrogen, in which case you're going to end up with aldehydes first, those are going to undergo oxidation to give carboxylic acid as well. So in that case, you would have gotten one of these compounds as a dicarboxylic acid rather than a ketone carboxylic acid. Anyway, let's keep going forward. The next question is that we have an aldehyde, and that aldehyde essentially contains 1, 2, 3, 4, 5, and 6 carbon atoms, and I'm supposed to convert that into a carboxylic acid containing the same number of carbon atoms. Realize that the problem here is that you have an alcohol and an aldehyde. So if you subject that to treatment with like KMNO4, for instance, directly, or any other oxidizing agent like PCC or something, it's going to want to oxidize both of these groups. So your first step should be to protect that primary alcohol. And the best way to do that is using TMS chloride. So I'm going to use TMS chloride triethylamine the way we talked about in class. Realize in this case it's going to first give you the O, let me write that, the OTMS, OTM, let's write it this way, DMS. One more time, TMS. And the rest of it is going to remain just the same. So 1, 2, 3, 4, 5, and 6. I don't want to be creating atoms here. And now you would be able to oxidize this. So you can use KMNO4 PCC, whatever you want. So KMNO4, let's say KMNO4. And the third step is after the KMNO4, you have to hydrolyze it. Like I said in class, you can either use hydrolysis as a step to remove the TMS, or you can use TBAF. In this case, the acid that you use, that should be plenty to get rid of both the TMS as well as the manganese, and so you will end up with the product that you have. The next reaction is that you have cyclohexene, and I'm subjecting that to the oxymercuration, demercuration version of synthesis of ethers. So realize you will start with the formation of that three-membered ring, and then the ring is going to open up. So in this case, you're going to end up with the ether, where you have cyclohexyl on one side and a propyl chain on the other. And we are going to use sodium borohydride to just basically cleave off that carbon-mercury bond to a carbon-hydrogen bond. And the next step is to be able to cleave that ether bond. So since you have iodine here, you're essentially treating it with HI and heating it to reflux, and that will give you the desired product. I think we can move over to the next slide now. So let's take a look. We have to convert essentially from this primary alcohol. I have to convert that to get an aldehyde. Realize 1, 2, and 3. So carbon number 1 is becoming the aldehyde. 2 and 3 are still where they are. The cyclohexyl follows, and then we have the ester here, which is getting converted into this tertiary alcohol. So hopefully you can see that you are getting a tertiary alcohol, and that must mean that at some point of time you have to go through a ketone. So let's take a look how that will happen. Hopefully you can see that this tertiary alcohol can be generated if you would have a ketone. Let's erase that. If you begin with an aldehyde on this side, and we have, notice, an ester, and we have to get a tertiary alcohol. So if you generated, let's say, this ketone first, and then used another Grignard reagent on that. So the question is, how can you convert the ester into this ketone? Notice I have just added an R group. The R group in this case is an ethyl group, so I must have incorporated ethyl magnesium bromide followed by hydrolysis, and I will need 2 equivalents of that for the reaction to take place. But realize that can be done provided this alcohol is protected, because alcohols have this acidic hydrogen of the OH, and that is going to interfere with the Grignard chemistry. We talked about that in class. So your first step should be to treat this starting material A with TMS chloride, and that will basically protect the primary alcohol, and that will generate the OTMS here. And after you have done that, you will then use 2 equivalents of the ethyl magnesium bromide. The reason why you know it's ethyl magnesium bromide is because you have 2 ethyl groups here, one right here, the other right here. So that means that you must have gone through this ketone that I'm trying to show you. And then the third step will be that we are going to get rid of the TMS group, which actually will be removed once you hydrolyze this. And then we are going to treat that with just a PCC to generate the desired aldehyde. Realize in this particular case, since we are getting a tertiary alcohols do not oxidize. So when you subject that to the PCC conditions, the alcohol will remain intact, so you don't have to carry out another deprotection strategy there. Okay, let's go to the next, and that is this slide right here. We are given, essentially it's a box problem type of a scenario. We are given several different reactions and we are supposed to provide the product of each of these. The first question is that we have an ester and we are subjecting that to reducing conditions. Reduction reaction is being carried out. Recall that lithium aluminum hydride is a strong reducing agent that's going to reduce that C single bond O, and at first you are going to get the aldehyde, but it's not going to stop there, and it's going to go all the way to the alcohol because this is a strong reducing agent. So you're going to end up with propanol and methanol, which is going to be obtained from this part of the molecule. So 1, 2, and 3, they're going to be here. So propanol is your byproduct. Okay, let's go forward. The next question is you're given a ketone which is being treated with sodium borohydride. You know, it's a reducing agent, it's a ketone, so your product should look like a secondary alcohol, which is right here. Next question is you have a primary alcohol. It's being subjected to a strong oxidizing agent now. So that's my Jones reagent right here. And the other one is DMP, the Des-Martin periodinane, which recall I told you in class that that is a weak oxidizing agent. It will only go up to the aldehyde stage, whereas if you have Jones reagent, it's going to go all the way to the carboxylic acid. Since you have total of 4 carbon atoms, you're going to end up seeing a carboxylic acid with the Jones reagent and an aldehyde in case of the Des-Martin periodinane. If you take it one step further, they're saying that we have treated it with Grignard reagent and excess. So realize sometimes they may not say 2 moles, but rather excess. And that means the same thing. It's just that it doesn't stop at the ketone and would rather go all the way to the tertiary alcohol. So in the first stage, you're going to, since your Grignard is delivering a methyl group, you're first going to end up with acetophenone. So that methyl will attack, electrons will move, electrons will come back. This OCH3 will leave, and this will further react with another CH3 MgBr, which is going to give you a tertiary alcohol at the end of the day, which will look like this molecule right here. All right, let's go forward. Let's take a look at the last problem. Is that we have an epoxide and we are subjecting that to treatment with an acid and a base. So hopefully you can see that in case of a base, we have an S negative, which is nucleophilic in nature too. It is going to attack the epoxide from the less substituted site, and essentially the epoxide will ring open. First, it's going to give you the ethyl group, the O negative, here the S ethyl group, and then that upon hydrolysis is going to give you the corresponding alcohol. So you'll get an OH with an ethyl, and on the opposite side, so if this is on the solid line, you better put the S on the dash line with the ethyl group, and that's going to be your product. Now, if this were an acid condition, it's going to go through the protonation. So you're going to first show, let's switch the color perhaps. So lone pair of the epoxide is going to attack and it'll protonate the epoxide. So your first product is going to be the positive charge on the epoxide. And now you have to think about how will the ring open. And so hopefully you can see that if bond, let's switch the color again, if the bond A breaks, then it's going to lead to a primary carbocation. If the bond B breaks, then it's going to lead to a secondary carbocation. And so since the secondary is more stable, you're going to end up with an OH. And since this says HCl, I'll have to show the attack for Cl negative. So you're going to get the ethyl group. On the other hand, if that would have said H3O plus, H3O plus, and they did not specify the conjugate base, then you should just use water, in which case you're going to end up with a diol as the final product. But in this case, it'll be like a chlorohydrin for this particular reaction condition. All right, let's go